Welcome back to part 5 of our series on random forests. So this series is all about predicting stock price direction using the random forest model in Python. So in our last video, we had officially built our model. We had fit the data to the model, and then we began the process of evaluating it. And so part of it was looking at certain types of metrics. So things like accuracy, things like our classification report, things like recall, precision, and all this is really doing is it's just giving you an idea. I just did all this work. I just did this entire modeling process. How well did it perform? And for the most part, it actually did pretty well. I mean, I would say, a 70% accuracy rate is pretty good. But you also got to kind of take that with a grain of salt, because part of it is, well, what are we predicting? We're just trying to predict whether a stock closes up or down. We're not measuring the magnitude of that particular movement. So, well, it moved up. Well, it moved up like a cent. Well, in some cases that's a lot. But again, we don't have that magnitude component. So there's less variation as to kind of what it could be. So that was pretty good. So we're going to keep going through the process of evaluating it. We're going to kind of see some different tools that we have access to. The next one that we're going to talk about is a confusion matrix. And this is actually something the paper uses. And so it's actually calculating a lot of the same things that we were doing up here. But what it also allows you to do is it allows you to take this information and put it into something like a graph, something like that, where it might be a little bit easier to interpret the results and things along that nature. Now, I will warn you, I don't know why, but for whatever reason, it doesn't make the graph perfect. I still got to figure out how to change the coloring to get something that works. I don't know if it was because I ran in Visual Studio and it just did something automatic, but just an FYI, it might be a little hard to read at first. Okay, something you do need to make sure is you need to import your confusion matrix and plot confusion matrix from the sklearn metrics module. And then it's actually really easy to create a confusion matrix. So all you do is you take that confusion matrix object and you pass through your y-test, so the testing portion, and then the predicted values. And then what I do down here is I just display it. And then the first thing that you'll notice, and I'll kind of just turn this off for a second so you can see it, it's just an array. And then inside this array are the different types of metrics that were calculated. So the first one are the true negatives. So that's right here. And then we have the false negatives. And then the true positives is down here. And then the false positives are right here. So that's kind of how it's ordered. So it is important to kind of understand, like, how is it ordered? Because otherwise, if you start trying to pull it and you're not pulling the correct thing, it will obviously give you the wrong number. And then I just kind of recreate what was in the actual module itself. And so they just calculated accuracy, precision, recall, and all that stuff. Up here, when you do a classification report, you don't actually have specificity. And so this is how you can calculate down here using a confusion matrix. So really all you're doing here is calculate the same metrics up above. But again, it's just showing you how to do it another way if you so choose. And then also what you can do is you can also plot a confusion matrix. And so again, this is part of the sklearn metrics module. With this one, you pass through your model. So in this case, we have a random forest classifier, our testing portion for each X and Y, our display labels. So in this case, it's down day and up day, and then normalize. So again, with normalize, if you set that equal to true, it's going to make it as a percentage component. So it's going to be in percentage terms. It's not going to give you these absolute values like that. And then all I'm doing here is I'm just setting the title and then stuff like that. So create graph to plot confusion matrix. And it's pretty nice. Again, the coloring can be a little bit off, and as you can tell, it's really hard to see that. And then this one is too. I don't even know honestly if it's there, but It's supposed to be. You can change the coloring manually, but I just haven't found a set that works that well. So you're gonna have to play around with it a little bit, but this is just showing you, if you want, you can plot your confusion matrix. Okay, so now we're gonna talk about the next topic. The next topic when we're evaluating our model is understanding feature importance. So the idea behind feature importance is you're trying to understand what features are helping explain most of the variation in the model, right? So for example, maybe you have one feature that does really well. I mean, explains like 40 or 50% of the variation in the model. Well, that's great. That means that one feature does a really, really good job of explaining the model. You might, on the opposite end, have a situation where maybe one of your features only explains like 2 or 3% of the model. It probably doesn't warrant keeping that feature because A, your model is just going to take a lot longer to run, and it doesn't seem like if I remove that feature that it's really going to cost me as much as leaving it in there. So part of it is a judgment call. I mean, it's not always clear cut sometimes. I will tell you, I played around a little bit with this, and I actually found when I removed the on balance volume, it actually was a little bit better somewhat, but it wasn't to say it was necessarily worthless. So I kind of put some little notes here when you're thinking about it, but part of it is it's not always clear cut. So I always kind of, the example might be something like, well, if I get rid of the feature, okay, well, it lowers my accuracy. And most people say, no, I don't want to lower my accuracy. It's bad. Oh, well, it lowers it from 95 to 92%. Okay, well, part of it really depends on the problem you're trying to predict. But for most people and most problems, that's more than okay. I mean, a 92% accurate model is really good. It's really, really good. So the difference between that 95 and 92, in most cases, it's not going to be that big of a deal. And you actually get some benefit of removing that extra feature in the sense of you don't have to sit and wait as long for it to train or X, Y, Z. So when you're thinking about this, you just need to understand that yes, there is a trade-off. I'm not going to tell you it's not a complete trade-off, but part of it is sometimes it doesn't really hurt you necessarily to get rid of it. So if you want to get the feature importance, it's pretty straightforward. So we're going to create a new variable. We'll call it feature importance. And there's my little attempt at making it all nice and pretty. And then we're going to pass through our random forest classifier. And then it has an attribute called feature importance. And then it is an underscore at the end. We're going to specify our index because we are doing a panda series. So I'm going to take my X columns and then I'm going to do the columns attribute. So that will return a list of the columns. And then from here, I do want to sort my values. I do want to do ascending equals false. And hopefully I spelled everything correctly. And then if I do this, looks good. Okay, so right now what we can tell is our K% is basically our most important feature. It does do, It does explain most of the variation. Apologies for this one. I wrote this a little bit before I added the on balance volume, but it is ordered in most of the explanation in the sense of how much does each feature explain the model. So we have K% and then R%, RSI, MACD, price rate of change. And for the most part, these are kind of relatively in the same range. I mean, yeah, these two, I would definitely call them, the bigger ones. On balance volume, 11%, it's not horrible, but, it was kind of interesting. Obviously, if you remove a feature, what's going to happen? Well, everything else should more than likely go up, right? So part of it is just, you got to understand, but then you also have to understand the minute you take one of these out, then naturally everything's going to go up. So you might be thinking, oh, well, this doesn't, really do that much or something. I will say this. I got rid of on balance volume and my accuracy stayed relatively the same. I would say, where was it again? I was maybe at like 65, 68%. So again, I removed it and it didn't seem to impact it that much. So, you might say, hey, actually, I don't need on-balance volume. Maybe it's not really as important as I thought it was going to be. The thing is, I have such a small data set, it really doesn't matter. So in this example, just leave it in. It's not going to really care at the end of the day. And the other thing is, though, too, is you don't want to just add features to add features. You really want to add meaningful features because, yeah, if you add something, naturally, it's probably going to go up, but that doesn't mean it's actually telling the story. So, just keep that in mind. Again, there's all these trade-offs that you have to think about. Something you also have to understand is, how is feature importance computed? Well, there's different ways of measuring it. One is Gini-based importance, and then one is accuracy-based. And so in my previous video, I talked a little bit when I was creating the model about the, GD index and stuff like that. And so I did want to take just a tiny bit of time to kind of give you an idea of kind of what's going on behind the scenes. And so I'm going to actually bring up some stuff here. I mean, me personally, I read through this presentation and I'm like, man, this just makes it really straightforward. And so for me, like I said, if this is something new to you, I would really encourage you to read through some of these presentations, because I think they just do a really good job of making sure everything is good. And so one of the first things I was going to tell you about is, when you're building the random forest algorithm, why does it do such a better job necessarily compared to like, bagging or stuff like that? And part of it was I said, okay, well, we have these we don't have these highly correlated decision trees. That was benefiting us because when they were highly correlated, they could overfit the model and stuff like that. And it wasn't really doing a good job of being used in future cases. And so with this one, why is that the case of doing that, right? Well, part of it is when you're going through the steps of building a random forest, when they're building the trees, step one is they take a random sample size n with replacement from data. So that's just, again, what we were doing before. And then step two is take a random sample without replacement of the predictors. This is the key part. This is where it's fixing things. Because it is taking a random sample without replacement of the predictors, this is Random Forest's solution to the highly correlated trees. It's the without replacement that is fixing the problem. And so this is why Random Forest is creating what you would call or is a better predictor and a more stable predictor when it comes to making these types of predictions. It's because that's how it's handling the particular situation of removing the highly correlated trees. So very interesting. Again, there's some mathematics behind it. They're all here. If you'd like to, look through it, by all means, go right ahead. And then something too I found online, because I wanted to give people, where is it? I thought, oh, here, this guy, he did a pretty good job. I liked how he did it. Mr. Victor Zhao, if you ever come across this video, you did a good job. He was talking about, at the top, we were talking about Gini impurity. And so this idea of impurity is when we're building our random forest, part of it is we have to split our trees, right? So we have to basically add more layers on our trees. And the question that naturally arises is, well, when do I stop splitting my tree, right? When do I stop splitting my tree? How do I know when to stop? Because can't you just keep going, going, and going? And so part of it is we look at this idea of impurity to determine when we've reached a point that the information gain has kind of been maxed out. And yeah, there might still be some likelihood of things potentially being classified wrong, but it's not as large as it was before. And so the thing about impurity, well, how do you think about impurity? Impurity is saying, what is the likelihood that I misclassify a result? So for example, if you want to do a really, really simple example, just say you have, basically a data set can be either on or off, right? So you would say the impurity is 50% ideally. I mean, it's a little bit less than that, But the idea is that, it's basically a coin flip, so the model has the capability of possibly being wrong 50% of the time. And so what the Gini impurity does is it measures, for example, if I keep splitting my branch, the idea is that I'm going to get something called information gain, right? And so that means that ideally my impurity should go down because now I have less of a chance of misclassifying that particular data set point. Now, again, there's some math behind this, but high level at this point, I just kind of want you to get the idea, which is if I split, I'm kind of reducing my impurity because there is less of a chance that we can misclassify it. And so the idea is you keep splitting it. So you keep splitting your tree. In the process of splitting it is you're going to reduce your impurity. That difference between the old impurity and the new impurity is now that information gain. And you keep doing this until you reach kind of like what you would call this optimal level. Now, technically, if you can get a Gini impurity of 0, that's the lowest possible value and the best possible value. But what that's also saying is that you only have one possible outcome. So it's all, on. There's no off scenario. So you have to keep that in mind. You're never really going to go to 0, but you want to get somewhere kind of, you're trying to get to this low level. Now, this is all kind of done behind the scenes for you, but you do want to understand what's happening. That's how it's deciding how deep to make its trees and how much to split in X, Y, Z. It's using this measure to say how many times should I split my tree? What am I looking at as I'm going on? The idea is that you have this concept of impurity, and impurity is just saying, hey, what is the likelihood that I could potentially misclassify a data point? Okay, well, if that's the case, if I add a new split, does my impurity go down? Okay, if it does go down, then what that means is that I basically have some information gain. So I have less of a chance potentially of it being misclassified. Now, again, there's some math behind this, and I'll be providing those documents for you. I don't want to get too much into that right now, but you basically keep doing this until you kind of get to that until you basically maximize that Gini measure. Now, I kind of like the way he kind of puts it, really what you're doing is you're maximizing the Gini gain. So the best split is chosen by maximizing the Gini gain, which is calculated by subtracting the weighted impurities of the branches from the original impurity. So again, there's some math components behind that, but again, this is what's being used behind the scenes to determine, how to split it in a certain sense. So again, just some background for you. I'm sure I confused some people in that, but it is good kind of to understand how it is. And that's really kind of how you're also determining your feature importance as well too, because that's telling you how much that's helping you explain in the information gain that you might be getting from it. Another way that you could also, if you want to kind of visualize this, is you can actually graph the cumulative importance. And so again, I kind of already have something just typed out, so I thought I would kind of just show people. Again, people like seeing information differently. Now, you could also, if you want, me personally, I found a line graph online. Maybe. I think it makes sense in a certain point because what they're trying to say is like, oh, your threshold is like 95%, right? You want to be able to, retain 95% of your feature importance, right? And so the idea is that if you have a ton of features, then if you have 95%, you can just get rid of the other ones and you don't need to keep the rest, right? Because then it's just kind of right. So, we already explained 95% of the model. So what's the extra 20 features going to do for you? That's simple terms, but there's kind of more to the story, as you could imagine. And so all this is doing is it's graphing a cumulative importance graph. And basically what we're doing here is we're just taking a cumulative sum using NumPy, and we're taking the values that we got from our feature importance. So pretty cool stuff, I think. It's just kind of building all the different features that we need from our model. And then we just kind of put our horizontal line, we have our X ticks, we got our label, our Y label, our title, and things like that. And then we also make sure we plot it. And so when you do this, you're gonna get something like that. And so you can kind of see like, okay, so, maybe we don't really need this extra one, but you can also kind of tell, for the most part, they're kind of all relatively close. You don't see anything like very curvish for the most part. So again, just another way of looking at the particular model. All right, so model evaluation. So there is this other type of graph we can use. It's called an ROC curve. So it is short for receiver operating characteristics. I just took this one, I think, off of sklearn. I thought they did a good job. So it's a graphical method to evaluate the performance of a binary classifier. The curve is drawn by plotting the true positive rate sensitivity against the false positive rate. So 1 minus the specificity at various threshold values. So the ROC curve shows the trade-off between sensitivity and specificity. When the curve comes closer to the left-hand border, so over here, and the top border of the ROC space, it indicates that the test is accurate. The closer the curve is to the top left-hand border, the more accurate the test is. If the curve is close to this 45-degree line, I'll show you kind of how to graph that next, of the ROC space, it means the test is not accurate. So ROC curves can be used to select the optimal model and discard suboptimal ones. So for example, if you were going to be testing a bunch of different models, right, and you wanted to see it, if you changed a couple of different hyperparameters and you're trying to identify which ones is really the most optimal model, you could use the ROC curve to determine that. So ideally, what you're looking for is this curve is going to get as close up here as possible. This is where you want it. You don't want it in this 45%. So the further away it is from right here, the better. You want it all the way up here. That's the good one. So that's really kind of the idea behind it. Again, they make it really easy to plot this. This is the new thing that I had to update my sklearn to leverage because it is in the newer model. Because it was such a popular graph, they kind of just standardized it for everybody, which was nice. So all you do is you call the plot ROC curve, and then you pass through your random forest classifier, your X test, and your Y test, and then your alpha. And there you go. And so you can tell, it's a little bit hard to tell. It's not horrible, it's not great, but as long as we're getting away from this horizontal line right here, it's better. It would be curious to see, hey, if we add more data, does this necessarily help? Does it get us kind of closer? This would all be something as you're looking back and saying, oh, I can't stand this. I need a higher or something like that. This is maybe a curve that you could leverage down the road in order to do that. All right, so the next score that we're going to talk about, this one, it's used. You'll see it kind of be used. Some people don't like to use it in tandem. Okay, so you'll hear some people say don't use this score in tandem with something like accuracy because it's really kind of two different things. You're kind of comparing apples and oranges. But there is this concept called the out-of-bag error score. So the OOB_ score uses a sample of the leftover data that wasn't necessarily used during the model's analysis. So when it's training it, it's basically taking a portion of that training set, and it's using it to compare it to the actual when it's doing the whole training process. And the validation set is a sample of data you decide to subset. In this way, the OOB sample is a little more random than the validation set, right? Because if I'm just randomly taking it as I'm training it, it's just, again, this idea of a little bit more random. Therefore, the OOB sample, on which the OOB score is measured, may be harder than the validation set. The OOB score may, on average, have a less good accuracy score as a consequence. Again, it's just kind of another way to look at it. Me personally, I think it's good. I mean, I think it's an interesting score to look at. Ideally, what you're looking for is that your OOB score is relatively similar to your accuracy score. you don't want the two very different, because then that's saying there's potentially an issue and you might need to kind of rethink how you're kind of splitting your data set. So ideally, your out of bag error score should be relatively the same. It's never going to be exact. Well, never say never, but it should be relatively close to your accuracy score. They're not going to be the same, but they should be relatively close. So this one, it's a little bit more random. So ideally, if this is almost a little bit higher, you would kind of say like, oh, okay, so it's just maybe the model's performing a little bit better or something like that. So again, just things to consider. Now, you do have to make sure when you create your random forest classifier, where was it? Where is it? Oh, here it is. You do need to specify your OOB score equal to true. Otherwise, if you call this line, it will not work. So you need to make sure you do that. Okay, so my previous one was like 0.68. Was that it? ControlEnter. Okay, so it's about the same. So again, it's within that that range, which is good. I'm probably going to reword this definition a little bit, but again, what you're kind of looking for is that they're relatively same to the accuracy score, but the idea behind the out of bag error score is it's supposed to be, I'm not going to say a little bit more accurate, but there's more randomness behind it, and so ideally it should give you kind of a better idea to a certain extent about how the model would perform with more randomized data. So that's kind of good. That's good, and then ideally too is if I'm trying to think the best way to say this, you kind of, in a sense, because if you're seeing something where this is changing, it means something isn't necessarily right. And so if you can improve this by doing something like, hey, maybe changing your validation set or something along that nature, that could be possibly an indication of something. So again, if this is something where it's staying relatively stable, you're fine. But if it's something where you're noticing like, oh, I've changed my validation set or something like that, or how I'm subsetting it, that potentially, you just need to keep that in mind, that potentially there might be a problem where if it's constantly changing, then potentially you might be in an issue where you're not subsetting it correctly. So just some things to keep in mind. All right, here comes the fun part. I got to keep an eye on the time too. Okay, well, I have to do this part because the next time I can't do it. Yeah, I didn't want to, but I have to. So we're going to talk about improving our model, right? So we built it, we did it, we think it's great, but we want to see if we could potentially make it better. How do we go about that process? Well, in simple ways, we just change some of the parameters or the hyperparameters of our model, right? And there's certain ones that we can adjust, if you want to call it that. And if we adjust it, ideally, we should see some type of performance improvement. And if we don't, we know, okay, well, maybe we've found the optimal value for that particular hyperparameter. So a few of the ones that we're going to be looking at is the N estimator, so the number of trees in the forest, the max features, so the number of features to consider when looking for the best split, the max depth, so the maximum depth of the tree, and then again, I'll kind of explain what the interpretation is for certain values. The min samples split, so the minimum number of samples required to split an internal node. Sample leaf, the minimum number of samples required to be a leaf node. And then bootstrap, whether you want to use bootstrap samples when you are using it. So very interesting stuff. What I'm going to do is I have a bunch of this already kind of plotted out, and then we can kind of go through some of the things that we can consider. Alrighty. Okay, so I'm going to be very vague to a certain extent, so bear with me. And estimators, number of trees in a random forest. So this is kind of a funny one, because when I was reading online, they're like, oh, well, you shouldn't tune it. You should just set it large enough, right? The idea here is it's ambiguous to a certain extent. You just pick a large enough number. That can vary, and that can obviously be interpreted many different ways. So, for example, maybe 100 is enough. Maybe I should do 200, 300, 500. You know, I think on one of the papers, he kind of gave you a number. Well, actually, funny enough, here we are. What he kind of says is, you know, the number you pick is really dependent on the sense of the size of the data, or based more on the data set itself. So that's really what should be dictating. But, you know, it's interesting because, like I said, they don't really specify what it is. They just kind of say you pick a large number of trees. He's kind of saying, well, you know, it kind of depends on your data set, but then he kind of doesn't provide like, well, what's the methodology behind it. So again, all I do here is I basically just create a list of numbers between 200 and 2000. So it's like 200, 400, and so on and so on. So for this one, again, it's just provide a list of numbers. Ideally, you want a larger number because the larger numbers it's going to be hopefully predicting more accurately, right? And then, hold on. I want to make sure So the other thing that you need to keep in mind is there's actually no risk of overfitting in random forest as you increase this. So you can add as much as you want, but it's not actually going to overfit the data set. So that's actually kind of a nice advantage. And then we have the numbers of features to consider at every split. So we have auto, square root, none, and log2. These are all the possible ones, so I just put them in. And then the maximum number of levels in a tree. So max depth is a parameter that most times should be set as high as possible, but possibly for performance can be achieved by setting it lower. So normally you want this high, but again, for performance considerations, you might sometimes set it lower because, you know, hey, if I set it just a tiny bit lower, my accuracy isn't changing that much. So I'm okay with that. But ideally, you want to try to be as high as possible. Okay, and then we have minimum number of samples required. So higher values prevent a model from learning relationships, which might be highly specific to the particular sample selected for a tree. Too high of values can lead to underfitting. Hence, depending on the level of underfitting or overfitting, you can tune the values of the minimum sample split. So too high, you're gonna go to underfitting. Too low, too high values can also land underfitting. So it can do kind of one of two things. You can also have underfitting or overfitting. So ideally is you can kind of adjust this as needed to hopefully improve your model in the process, but you just kind of have to understand how it's impacting it. Okay, so then we have minimum number of samples required at each leaf node. I just picked one. They said it could be anywhere between like 1 and 20. I think there was like this research paper I found online. And I think this one was like 2 to 50, but I stopped at like 40 or something like that. And then for bootstrap, I just did true and false, so just both. And then what I do is I create a dictionary where the key is the name of the parameter for the model. So in this case, if I'm doing random classifier, it would just be an estimators. And then I pass through the possible values that I want to do. So I do this, which is fine. Whoops. So we're good there. And then this is the fun part, because this is the part where you guys don't have to go through this. I do. Well, you're going to have to go through it at some point. This is where we actually find the most optimal one, right? So we create a new instance of our random forest classifier. We then call our random search cross-fold validation object. This is basically going to take a bunch of different combinations and test it and see what happens. So it's going to basically take that parameter grid that we had up here, and it's going to take our random forest classifier, and it's going to try a bunch of different combinations, and then it's going to do cross-validation to let us know, after running a bunch of times, what the optimal parameters are. And so the first argument is your estimator, which is your random forest classifier, which we have right here. The next one is your parameter distributions. Well, that's just your random grid. You have the number of iterations. The higher you set this, the longer it takes because it's going to do more jobs. So you just got to keep that in mind. And then CV is the cross-validation strategy. And so I think the default is 5. I set it to 3. I mean, we could set it to 5 and see what happens. Verbose is going to tell you how often you get a message down here. So higher number, you're going to see more messages more often. I had it at 2, and you can kind of tell 45 seconds, 4 minutes, 8 minutes, so on and so on. So I'll put it at like, I don't know, 5, just kind of see what happens. Random state is your random state number generator. And then number of jobs is the number of jobs in parallel. If you do it -1, it means all processors. And then you basically just take this wonderful thing and you fit the data to the model and you should be good to go. So what I'm going to do is I'm going to run this. Hopefully that works. Okay, it's running perfect. So that is currently running, and I will cut the video off here, and then when you come back, it should be done. And then we'll go on to the final one and we'll see how it did and see if it approved it. So if you have any questions at this point, feel free to put them down below and we will try to answer them as best I can. And then I think that's pretty much it. And then we'll wrap up the series with the next one. So thank you again for watching, everybody. We'll see you in the final video, and then hopefully you can see what's going on here, right? Wonderful.